Welcome, everyone. Stephen and I are both engineers working on the Cloud Foundation team at Airbnb. In today's case study, we're excited to walk you through Airbnb's Istio journey. To understand why we started the journey, let's take a trip down the memory lane. Since 2013, Airbnb has been using a service discovery system called SmartStack that we open sourced. On a high level, SmartStack uses Zookeeper as the service registry and relies on a bunch of sidecars to read and write service discovery data from Zookeeper. Started out as a simple yet effective system, SmartStack had served us well until a few years ago. Over the years, we added more and more functionalities to SmartStack. Here's some examples. We added support for Envoy as the data plane proxy in addition to HA proxy. We added MTLS support. We supported Kubernetes in addition to EC2 workloads. In the end, we ended up with 4 init containers and 6 sidecar containers for SmartStack to work on Kubernetes, resulting in the complexity and maintenance costs to explode. To make matters worse, as the size of the mesh grew and the rate of changes in the mesh increased, both Zookeeper and sidecars started seeing scalability issues. In 2019, we decided to stop patching SmartStack and search for a modern service mesh solution with the following requirements in mind. First, the new service mesh must be able to propagate changes quickly and scale to tens of thousands of managed proxies. The new service mesh must provide complete security features like MTLS and cert rotation. For data plane proxy, we preferred Envoy as we had in-house operational expertise with it as the secondary proxy for SmartStack. We'd also like the new service mesh to provide rich features in traffic management, resilience, and observability. And last but not the least, the new service mesh must support Kubernetes as well as EC2. After a few rounds of research, Istio quickly came up as the top contender. We really like the comprehensive security solution provided by Istio. Being able to continue to use Envoy as the data plane proxy is also a key selling point for us. Istio's rich features would save us a ton of time to reinvent the wheels. And last but not least, we like the active and engaging Istio community. At the time in 2019, we also had a few concerns, including performance and scalability, multi-cluster support, and VM support. Istio improved a lot in performance since 1.1 release. In Q4 2019, to verify these improvements, we performed a large-scale control plane evaluation on Istio 1.3 with multiple Kubernetes clusters and up to 60,000 connected proxies. The results established our confidence in Istio being able to handle the scale Airbnb needs. As Airbnb has a few dozen Kubernetes clusters in production, another concern we had was around multi-cluster support. We knew very early on that we wanted to do an external Istio deployment for the following reasons. First, we'd like tight access control for the control plane. Second, we'd like to isolate control plane components from data plane workload. And third, we'd like ease of operation provided by the central control plane. We had to solve a few problems to get an external Istio deployment to work on Istio 1.5. We solved multi-cluster DNS by using external DNS to sync service IPs to Route 53 and use Route 53 as the main DNS server for workload clusters. We are interested in trying out the smart DNS feature once it's more mature. At the time, Istio CA didn't work for multi-clusters. We had to run Istio D in workload clusters for CA and sidecar injection. We filed issues for all these problems, and all of them are fixed in subsequent Istio releases. In early 2020, mesh expansion on Istio was very manual. We evaluated 2 options to support EC2, including building a ZK plugin for Istio. We didn't go this route because we no longer want to maintain Zookeeper. Second, building a custom sidecar and Kubernetes controller to update service entries. We built a prototype and originally planned to contribute to the community. In the second half of last year, we learned a few upcoming features around VM health check and auto registration. We decided to discontinue the in-house implementation. Stephen will talk more about our setup in a few slides. Here's the final Istio architecture we landed on. It's being used active in production today. As mentioned previously, we run Istio-D in a dedicated Kubernetes cluster. Only control plane components run from this cluster, and only mesh administrators have permission to this cluster. We added a simple configuration file Airbnb engineers interact with. The Istio CRDs will be generated from this configuration file as part of the CI. The generated CRDs will then be deployed and managed by our deployment system. All Istio configuration changes are monitored and can be easily rolled back. Within a single mesh, we run a flat network. Kubernetes pods across Kubernetes clusters are assigned VPC IPs and communicated directly. We handle the EC2 workloads in a similar fashion. Today, Airbnb runs in a single region. We are working actively to run Airbnb from multi-regions. We will be running 1 or a few meshes per region depending on the size of the region. And one mesh does not know about workloads in other meshes. Cross-mesh traffic will be routed to the ingress gateway running in the destination mesh. As the gateway is managed by the destination mesh, it knows how to forward the traffic to the destination pods. To securely handle multi-region traffic, we need a strategy to authenticate between regions. To ensure a CA in one trust domain cannot forge certificates from another trust domain, we enforce name constraints in our CA hierarchy and deny access by default access model. For each region, we assign independent root CAs with trust domain locked name constraints. The intermediate CAs used by Istio is signed by the root CAs in each region and can only issue workload certificates with corresponding name constraint. This approach allows for flexibility around TLS termination location while keeping identity and authentication secure in the face of potential attackers. The hardest part about any infra project is migration. We'd like the new service mesh migration to be safe and easy. As a result, we support edge-by-edge migration, where an edge is defined as a logical edge in the service mesh from service A and to service B. A service should not require a leap of faith when onboarding the new service mesh. It should be able to migrate each of its edges one by one, starting from the least important edges. And for critical edges, we support percentage-based traffic shifting from SmartStack to the new service mesh, allowing side-by-side comparison of error rates and latency. In case anything goes wrong, service owners can quickly roll back. Throughout the migration process, we provide tooling to generate the migration configs automatically. Here's how the traffic shifting works on a high level. First, we run Istioproxy alongside SmartStack sidecars in shadow mode. We then configure Istioproxy to intercept traffic going to the reserved CIDR ranges for the new service mesh. Then we added traffic shifting capability to Airbnb's standard HTTP client. To shift traffic from SmartStack to the new service mesh, a service owner can simply increase the traffic percentage using our dynamic configuration system. And as traffic is being ramped up, the service owner has access to a migration dashboard tracking the changes in error rates and latency. Now I'm going to hand over to Stephen to talk about Istio upgrades.
Thanks, Weibo. I'll now talk about upgrades. Istio publishes 4 minor releases a year, and so far, there have been a lot of changes with each release. We upgrade soon after new minor releases, and as soon as possible after security releases. We aim to minimize toil and catch operational safety issues as early as possible in the upgrade process. And we break this process down into 4 main steps. First, we build the proxy, then we generate Istio manifest files, then we do control plane deployment and integration testing, and finally, data plane deployment. First, let's talk a little bit more about how we build Istioproxy. Airbnb maintains a couple of internal Envoy filters, which provide custom metrics. The filters need to be compiled into the binary, so we can't directly use the open source Istioproxy image. We also modified the Envoy bootstrap config file slightly to add custom metric tags, but now that extra stat tags is available in Istio, we plan on switching to the open source bootstrap config. Our internal Envoy repo contains custom filter code, the modified bootstrap file, and Bazel files, which pull in the Envoy source code and build dependencies. Our CI jobs build Envoy and the Istioproxy image, then uploads them to artifact storage. Upgrading the proxy image involves changing Envoy and Istio commit references in our Bazel files and updating bootstrap file. Next, we'll talk about manifest generation, or how we create the Kubernetes objects making up the Istio control plane. Most of our manifests are created by calling the istioctl manifest generate command. The outputted manifests are customized by Istio operator specs. We use the default profile and then always pass in a base operator spec, which has settings common to all types of Kubernetes clusters. Additional operator specs get layered on top. These are more specific to the type of mesh and cluster we are installing Istio on. The top right gray box shows our sandbox mesh setup, which is single cluster and ephemeral. The bottom gray box shows a production multi-cluster mesh, which has operator specs for the management cluster and workload clusters. In addition to using operator specs, we directly concatenate custom objects such as mesh-wide Envoy filters to the manifests. For upgrades, we download the new version of istioctl, update operator specs, and generate manifests, which get checked in. This lets team members perform code review on changes compared to previous versions before deploying. Istio supports canary control plane deployment since 1.6, so most control plane object names are suffixed with the revision. However, objects such as RBAC configs and custom resource definitions are not suffixed and have a blast radius affecting all control plane revisions. So we check changes to those objects particularly closely. After manifests are checked in, we start control plane deploys. First, we deploy to the sandbox mesh and run integration tests to check for regressions in Istio. Next, we deploy to the test mesh, which runs some toy workloads which generate traffic. And finally, we deploy to the production mesh. In the last slide, I talked about running integration tests before deploying the control plane to prod. Let's talk about some of the test cases that we check before each control plane and data plane deploy. The most important features are around the overhead of the data plane in terms of resource consumption and latency. We also test key security, resilience, and traffic management features. We use Fordio heavily as a workload, both for load and functional testing. Our test cases are also parameterized so that we can easily extend their coverage as we use additional features in Istio. By performing end-to-end tests in a pre-production environment, we were able to catch several bugs so far. We either submitted issues or fixes in each case. After the control plane is rolled out, we start upgrading the data plane. You can upgrade a Kubernetes deployment or other workload by changing the revision label on the pod template. When pods are created, the new Istio injection webhook gets called. However, we need a safe and scalable way to upgrade thousands of workloads. Our solution leverages an internal tool called CRISPR, which controls rollouts of pod mutations. The mutation in this case is trivial. Only the pod's revision label is changed, and the Istio sidecar injector continues doing most of the heavy lifting. The rollout functionality of CRISPR is more important for us. Most of our workloads use standardized namespace suffixes, so CRISPR allows us to select the revision label based on these suffixes. For a given suffix, we can also split revision labels by percentages. For example, Pods in 25% of namespaces ending in staging might use revision 1.6.11, and the remaining 75% would use 1.6.9. Namespace suffix matching and percentage rollouts give us fine-grained control over how proxies connect to the new control plane. In addition, because CRISPR runs as a mutating admission controller, we can rely on regular node and pod rotations to gradually update the proxy and pods without forcing all service owners to redeploy. You can read more about other features and design decisions made by CRISPR in our blog post. Let's step away from testing and upgrades to talk about our strategy around supporting VMs on Istio. Like many companies, Airbnb has a number of workloads which are hard to run on Kubernetes for various reasons, so this is important to us. Here's a high-level feature comparison of running Istio on Kubernetes and Istio on VMs as of 1.5. The two biggest gaps for us were that there was no automation for adding and removing VM instances from a service, and that there was no support for checking whether instances were healthy and ready to serve traffic. By the time Istio 1.8 was released, two key features made VM integration much more promising. Workload entries and workload groups were introduced. Workload entries represent individual running instances of VMs and are automatically created from workload group templates by IstioD when a proxy connects from a VM instance. Workload group readiness probes allow for active server-side health checks of VM health endpoints and can dynamically add and remove endpoints from an Istio service. Now that we've covered the evolution of VM support in upstream Istio, let's do a quick rundown of how we provide each of these pieces of functionality at Airbnb. For installing the proxy, Istio provides Debian and RPM packages. We want to use the same custom Envoy filters that we use in Kubernetes, so we can't directly use those packages. Instead, we bundle up our custom Envoy, pilot agent binaries, and a few other files into a custom artifact. For configuring the proxy, Istio offers a sidecar.env environment variable script that can change the behavior of pilot agent. You can also run the istioctl x workload entry configure command to automatically set environment variables. Since Airbnb is building a custom proxy artifact, we opted to instead create a proxy run script template, which is rendered for individual workloads. This also integrates slightly better with our internal tooling. For PKI bootstrapping, istioctl x workload entry configure also provides a token in a CA, but it's up to users to transfer them to the VM that they will be used on. We built some internal tooling which runs on each VM instance and regularly fetches the CA and token directly from Kubernetes. Finally, we directly use workload group readiness probes and auto-registration. In addition to the functionality mentioned in the previous slides, we have a few more priorities to reach parity between our VM and Kubernetes Istio setups. First, we want to be able to upgrade the data plane seamlessly. Second, we have built some internal abstractions which condense workload group boilerplate and shield some of the details from users. Finally, we're working on enabling safe edge-by-edge migration with traffic shifting. We've covered a lot about how we're currently using Istio at Airbnb. Let's talk about how we plan on using it in the future, as well as some takeaways from this talk. First, we're going to continue expanding our usage of resiliency features. Right now, we're making use of retries, outlier detection, and locality load balancing, and we hope that adaptive concurrency control can be added as a feature soon. As Weibo mentioned, we're going to build meshes in many regions, so we'll make more usage of gateways for cross-mesh traffic. Finally, we'll support a larger variety of workloads as we migrate from SmartStack to Istio, including TCP and gRPC services. And here are our takeaways. First, we're happy with Istio's extensibility, feature coverage, and scalability. Second, we've appreciated the choice of using a centralized management cluster across a multi-cluster mesh, and we encourage others to do the same. Third, it's a good idea to have one or more additional pairs of eyes on manifests before they get deployed, even if you're using a canary control plane. And speaking of which, always use a canary control plane and gradually roll your data plane onto the new one. Fifth, test the features you use in a pre-production environment. Nobody cares more about your services than you and your team. Sixth, if you're moving from another service mesh or from no service mesh onto Istio, try to migrate your traffic edge by edge to catch issues without risking all of your production traffic. Seventh, if you're using VM support on Istio, definitely check out auto registration and health probes. And finally, make sure to engage with the community. They've been welcoming and responsive, and we've been happy working together. Finally, Airbnb is hiring. Please check out our website for open positions. Thank you.